Hello students, and welcome to this next session in the continued series of class 11th physics revision sessions. Uh, we have discussed in the last three sessions about the fundamentals and some applications of Newton's laws of motion along with friction. And today's session is a discussion and assessment session for the same, with which we will finish this topic of Newton's laws of motion and friction. So let's move straight ahead. So we will start with an example problem involving friction first. Okay, so we return to a type of problem we have seen earlier, but we had seen this situation wherein there was a slight change, as in this the inclined surface on which the smaller block is lying was also a smooth surface. But today we will look at a variation of this problem, where the inclined surface on which the block is lying, on the wedge that is having a coefficient of friction mu and therefore is rough, whereas the horizontal surface on which the wedge, the triangular wedge is placed, is a smooth surface. And in this particular question we will look to find the range of F, that is the horizontal external force that can be applied on the wedge so that the block remains stationary with respect to the wedge. So because there is friction involved now, we will see that there are two extreme situations in which limiting friction will act, and between those two extreme limiting situations there is a range of force that can ensure that the system will move in such a way that the block does not slip with respect to the wedge. So this becomes a slightly more complex version of the problem we've done earlier, because of the friction involved between the rough surface of the triangular wedge and the block, and therefore the two limiting situations that I was talking about. Okay. So let's understand the statement of the question first, and then we'll come to it. So we have to find the range of values or the range of magnitude of a horizontal external force that can be applied, okay, so that the block of mass small m does not slip on the wedge capital M surface. Okay. So let's say that we are given the values of capital M, small m, theta, the coefficient of friction mu, and of course acceleration due to gravity, and we have to find this range of force. So these quantities are given to us. Okay. So now it again comes down to understanding the free body diagram of the smaller block in the non-inertial frame of the wedge and applying the condition that the block should not slip. So suppose we assume that the wedge along with the block on it is slipping with some acceleration A, such that the block is not in motion with respect to the wedge. So this whole system has a common acceleration. It moves like a common body. Okay. So if you look at this as a free body diagram in the inertial ground frame, okay, so assuming no slipping, assuming the block small m does not slip with respect to the wedge capital M. So we will understand very easily that the horizontal external force that we are applying, that is the only horizontal force acting on the system. The other forces are all vertical, and therefore we will understand that the magnitude of this force should be equal to M plus M into A, provided of course that this statement is correct. So we have this as our first relation. Now we have to find the condition on A so that the block does not slip with respect to the wedge, and for that we will involve limiting friction and etc. So next thing we will look at the free body diagram of the block small m in the non-inertial frame of the wedge. Okay, so let's look at that. So our non-inertial frame of the wedge is moving with this horizontal acceleration A. So now on our block, which is placed on that wedge's surface, which should be at rest in this frame, it should be in equilibrium in this frame, should not be slipping. So the first force we will show is the pseudo force. The pseudo force. Okay. Then of course we have the regular forces like the gravitational force, the normal contact force, okay. Now the thing is that if the pseudo force is comparatively less in magnitude, it's at the lower end of the range of values because the acceleration is at the lower end. So we can assume that the mg sine theta component of weight will be dominating over the pseudo forces cos component, and therefore the block has a tendency to slip down the inclined plane. So assuming, okay, mg sine theta is greater than ma cos theta, so the tendency to slip is down the inclined plane. Okay. So in that case, the direction of the static friction that is preventing slipping will be up the inclined plane, trying to prevent it from slipping down the inclined plane. So without getting into too much of bother about resolving the forces, or let me just resolve the forces, that's also fine. So after resolving the forces, you will see that pseudo forces cos component acts like this, pseudo forces sine component acts like this, mg's sine component on the other hand acts down the inclined plane, whereas mg's cos component acts normal to the inclined plane. The normal reaction is in this sort of direction, and the most important thing for us now, the direction of friction is like this. Okay, so this is after resolving the forces. So we can see that the condition for the equilibrium becomes that mg sine theta is balanced by the sum of ma cos theta and static friction, and normal reaction balances the sum of mg cos theta plus ma sine theta. That is the second condition. And now the limiting condition on friction for us becomes the important equation. The limiting condition of friction is that static friction should be less than equal to mu n. So when we incorporate this limiting friction condition by substituting these values here, we can see that on the left hand side, the static friction required is the difference of mg sine theta and ma cos theta. This is the amount of friction that should be acting to prevent it from slipping. Whereas on the right hand side, the maximum friction available to us, the limiting value of friction is mu into n, where n from the second equation is mg cos theta plus ma sine theta. So this, as you can see, this equation rearranged now will give us a condition on A, and that condition will give us the limiting condition for the minimum value of A. If A is less than this, then we will not have enough pseudo force to generate enough friction to prevent the slipping down the inclined plane. So this equation, this inequality now is going to give us the lower limit of A, or the minimum possible value of A, which we will get by just rearranging the terms. Okay, so cancelling m, which is equal on both sides. Okay, keeping the terms of g on the left hand side. So we have g sine theta okay, minus mu cos theta. Now on the right hand side, if we keep the terms of A, we have cos theta plus mu sin theta. So we have this equation now. Sorry, this is an inequality, so this will be, okay, less than equal to. So if we just reverse it to find the value of A, so A is coming, the condition on A is coming that A should be greater than equal to G into this fraction sin theta minus mu cos theta upon cos theta plus mu sin theta. So this becomes the limiting condition, and from this we see that the minimum possible acceleration for the no slipping case should be this. Okay, so this gives us the minimum condition. I'll just give you a minute to go through this working before we come to the next part. Okay, now coming back to the same situation. Now we will look at the free body diagram under the condition that this time the pseudo forces cos component exceeds the weight sign component. So basically what we are saying is that the acceleration of the system in the ground frame is so much that in the non-inertial frame, the block has actually got a tendency to slip up the inclined plane. So in that case, static friction will have to work in such a way that it opposes the tendency to slip down the inclined plane rather than opposing the tendency to slip up the inclined plane. Okay, so let's understand that. Okay, so what we are looking at is in this same situation of the other forces, that is pseudo force, the weight and normal reaction. Now suppose the condition for us here is that pseudo forces cos component is greater than mg sin component. So that means the block has a tendency to slip up the inclined plane. So in that case, what will happen is that static friction acts down the incline to prevent slipping. Okay, so in the free body diagram now, the direction of static friction should be such that it opposes ma cos theta and supports mg sin theta. Sorry. So this static frictional force will be acting in this direction. Okay. So once again, if we look at the forces after resolution, these are the components of the pseudo force. These are the components of weight. This is the normal reaction, and finally the static friction acts in this direction. Now, one of the reasons why I wanted to discuss this question is because now we will also use a sort of shortcut trick for solving the equations for this. And that shortcut trick is that now when we are applying the condition that, static friction plus mg sin theta balance ma cos theta, and normal reaction balances mg cos theta plus ma sin theta. And we have the limiting condition on friction, that friction is less than equal to mu n. So we substitute from both these equations that required static friction is ma cos theta minus mg sin theta. That should not exceed the limiting friction available, which is mu into normal reaction, which is mg cos theta plus ma sin theta, and we proceed this way. So finally we'll get a condition on A over here, that A should be less than equal to g into sin theta plus mu cos theta upon cos theta minus mu sin theta. Now the point I was going to make is that this particular equation could have come by just using a simple shortcut trick, that since the direction of friction has got reversed, because it's the other way around now, it has a tendency to slip up the inclined plane. We can directly get that relation by just reversing the direction of friction in this particular inequality. So that would mean that we want to replace mu with minus mu. And you can see that when we replace mu with minus mu, it means that in our free body diagram, we have reversed the direction of friction. So we would come to this equation directly. So that's a little trick that we can use, that instead of writing all these equations and coming to this conclusion, we can just simply understand that, okay, we have reversed the direction of friction in the FBD. So in the equation that we got in the earlier FBD, if we just reverse the direction of friction, that means effectively in our equations, wherever mu comes, we replace it with a minus mu to reverse its direction. And that would give us directly the condition on A. So now we are getting the other limiting condition, the other extreme condition on A, that A can have a maximum value. It should not exceed this value, that is of g into sin theta plus mu cos theta upon cos theta minus mu sin theta. Okay. So if we put together this equation with the one that we got earlier, we can see that A should be within this range of minimum to maximum. So the minimum was g into sin theta minus mu cos theta upon cos theta plus mu sin theta. And on the other side, the maximum in the limiting condition is this one. Okay. And also analyzing this, now we can say that therefore F should be less than equal to m plus m into this maximum acceleration and greater than equal to m plus m into the minimum acceleration, where we can just substitute the values of a minimum and a maximum as per this equation and the one above. Okay, so that completes this analysis. So I will just give you a moment to go through this once more and we will discuss further. All right, next up, we will discuss a problem with multiple blocks and friction between them. So this is another standard type of problem at JEE Advanced level. So let's see the situation in which we have say 3 blocks placed one on top of each other like this here. Let's assume the ground to be smooth, and these have masses like this, and this coefficient of friction is mu A, let's say, and this coefficient of friction is mu B. So given are the values here, M1 is 2 kilograms, M2 is 3 kilograms, and let's say M3 is 10 kilograms. This coefficient of friction is 0.4, and this coefficient of friction is 0.2. Okay. Now let's say what we're doing here is we are applying an external force horizontally on this block, and we want to find out under certain circumstances the acceleration of the 2 blocks, or rather the 3 blocks. So we want to find so in the first case we'll take the magnitude of this force as 7.5 newtons. In the second case we will take the magnitude of the force to be 60 newtons. Okay. So just take a minute to understand the question and we will discuss about it. Right, so the first thing we'll do here is we will analyze in general the direction of frictions that act on each of the blocks. So what we realize is that the moment we apply a pushing force on the middle block towards the right, it has a tendency to slip towards the right, okay, because of that external force. So immediately on both the surfaces of contact that it has, both with the upper block as well as with the lower block, the friction acting on it acts to oppose that. Okay. So the direction of friction acting on the upper surface of the middle block will be backwards. The direction of friction acting on the lower surface of the middle block will also be backwards. So these frictions are, let's say, FA and FB respectively. Therefore, on the other 2 blocks, that is on the upper block, the friction will act in this direction, and on the lower block, the friction will act in this direction. So this is how the direction of frictions is determined from the direction of the tendency to slip. Okay. Now we can also see that FA, okay, it has a maximum value. So the vertical forces, let's first figure these out. Okay. So NA is equal to the weight of this block, which we can see will be 20 newtons, taking the value of G as 10. And NB will be equal to the sum of Na plus the weight of the second block. So that will become 50 newtons. Okay. So from this we can see that FA's maximum possible value is equal to mu A NA, which will be 0.4 into 20 or 8 newtons, whereas FB's maximum value possible will be mu B into NB. So mu B's value was 0.2, so that will be 10 newtons. Okay. So from that we can understand one thing very interesting is that if you look at the acceleration of the first block, the acceleration of block M1 is equal to this friction divided by its mass. You can see that A1 should be less than equal to, because this friction cannot exceed 8 newtons, 8 by 2 or 4 meters per second square. So this is going to be an important value for us, that no matter how much force we apply on the middle block, A1 cannot exceed 4 meters per second square. Similarly, if we look at the lower block, its acceleration is completely dependent on the friction FB. So that means that the maximum possible value of A3 is less than equal to 10 divided by its own mass, which is 10, or 1 meter per second square. Okay. So no matter how much force we apply on the middle block, this upper one cannot go faster than 4, and this lower one cannot go faster than 1 meter per second square. So that will become an important part in our analysis. So once again, if you just go through this once before we proceed next. Okay. So A1's maximum possible value is 4 meters per second square. Similarly, A3's maximum possible value is 1 meter per second square. Because remember, here we have used the values given to us. M1 was 2 kilograms, M2 was 3 kilograms, M3 was 10 kilograms. This coefficient was 0.4 and this other coefficient was 0.2. So just make, make sure you understand these two maximum values, then we will proceed from here. Okay, so once we have understood these limiting values of accelerations, now we can see it's easy to analyze whether or not slipping will be taking place when we apply these forces. So when I'm applying the external force of 7.5 newtons, okay, if I assume that there is no slipping at either surface of contact, then I can make a combined free body diagram for this whole system. And see that common value of acceleration. So suppose I take that as A. That common value of acceleration should be F divided by the net mass. So that would be 7.5 divided by 15 kilograms. So that would be 0.5 meters per second square. Now rest I don't really need to do so much, because I've already seen that A1 should be less than equal to 4 meters per second square. So that condition is getting satisfied here. Okay. And I have also seen that E3 should have been less than equal to 1 meter per second square. And that condition is also getting satisfied. So that means my assumption, so this implies that my assumption is true. Okay. And what will happen is that they will have this common acceleration. In fact, FA will be equal to M1 into this common acceleration. So that will be 2 into 0.5 or only 1 newtons. Whereas we saw earlier that FA could be up to 8 newtons. So we know that 1 newton is definitely available to support the no slipping condition. Similarly, FB is equal to M3 into A. So that is going to be 10 into 0.5. So that is 5 newtons. And we had seen that FB could go up to a maximum of 10 newtons. So again, we can see that this condition is very much all right. So in fact, this is the amount of friction that will be acting at both the surfaces of contact. And this will be the common acceleration. But when we come to the second part, where we have taken the magnitude of the force increased to 60 Newton now from 7.5. So you can see it's quite a big jump. So for F equal to 60 Newtons, if we assume the common acceleration again, that common acceleration will come out to be force divided by the combined mass. This time it will come out to be 60 divided by 15 of 4 meters per second square. So you can see that this condition will not be satisfied because E1 was less than equal to 4. So that's fine. But E2 or rather E3, E3's maximum possible value was only 1 meter per second square. So this condition is not getting satisfied. So first of all, we will understand that therefore there is slipping between M2 and M3. That is, this friction will be a kinetic friction. So now, given that we are sure of that, let's find out what's happening between M1 and M2. Okay, so now assuming E1 is equal to A2 is equal to A, suppose. Okay, so no slipping between M1 and M2, assuming this. So we will take the combined free body diagram of M1 plus M2, on which we have applied this force, and there is kinetic friction FB acting. They should have this acceleration A. So F minus this kinetic friction here should be equal to the combined mass into a common acceleration. So 60 newtons minus 10 newtons should be equal to 5A. So we will get the value of A as 50 divided by 5. That is 10 meters per second square. So you can see again this is not possible physically, because M1's maximum acceleration, that is A1, was less than equal to 4 meters per second square. So that again means that our assumption that M1 and M2 are moving together without slipping, this assumption also fails. So now there is slipping between M1 and M2 also. So A1 is not equal to A2 is not equal to A3. And FA and FB are both kinetic frictions. So this is what we realize finally here. So on M1 there will be kinetic friction, giving it an acceleration A1, and that A1 will be this, which we already know is 4 meters per second square. Whereas on the second block M2, we are applying this force of 60 newtons. There will be kinetic friction here of 8 newtons acting, which we have calculated earlier. There will be kinetic friction here of 10 newtons acting, which we have calculated earlier. And this will give this an acceleration A2, which we will now find out. So F minus the sum of these two kinetic frictions will become the second block's mass into its acceleration. So 60 minus 8 minus 10 will be equal to 3A2. So A2 will come out to be 42 by 3, or 14 meters per second square. Whereas E1 was only 4 meters per second square. And now the third block, this has frictional force equal to its kinetic value, limiting value. Okay. So this will have an acceleration A2, or rather A3, which we know is going to be 1 meter per second square. So there's going to be slipping everywhere, and they will have individual accelerations of 4 meters per second square, 14 meters per second square, and 1 meter per second square respectively. So this is a more complicated version of the multiple blocks with slipping or with friction between them over here. So just make sure you take a minute to understand this solution properly, and we'll move on to another question next. Okay, the next question I want to discuss related to friction and Newton's laws of motion. Now, this will combine the concepts of constraint relations for a multi-pulley system along with the concept of friction. So let's just go through this. Okay, so we have this system over here where three block system with also a system of pulleys, the thread going around this one. All the pulleys are massless and smooth, and the thread is of course inextensible and light. Now this inclined plane has a coefficient of friction 0.5, whereas this other horizontal surface is smooth, and take the value of acceleration due to gravity to be 10 meters per second square. So we want to find the accelerations of these blocks. So just take a minute to try out this question and we will discuss. All right, so trust you would have worked out this question, or at least its concept by now. So you can see that tension acting within the system like this So you can also see that if we apply the virtual power method or the virtual work method for constraint relation, A has a motion down the inclined plane, C has a motion horizontally, and B has a motion vertically downwards like this. We will get the constraint relation here, that acceleration of A plus acceleration of C will be 2 times acceleration of B. So this is the constraint relation. The easy method of getting the constraint relation is by applying what we've discussed earlier as the virtual work or power method. If we go for the power method, we'll see that the power delivered by tension on A will be T into VA, assuming it has the velocity in the same direction as acceleration. The power on B will be minus 2T into VB, and the power on C will be plus T into VC. This total power should be 0. So that will give us this relation, that VA plus VC is twice of VB. And then on differentiating this particular relation, we will get a relation 1. Okay. And the rest, of course, is about understanding the free body diagram. So we'll just show the other forces directly over here. So you have weight of A, similarly C and B. And then we have a couple of normal reactions, one acting on A, which will be normal to the inclined surface, one acting on C, which will be vertically upwards, and finally there will also be a kinetic friction acting on A, because that is a rough surface, as we have seen. So now we can write the additional free body diagram equations for each one. So for the block A, we can see that T plus its weight sign component minus kinetic friction on it is equal to mass into acceleration. Okay. Whereas normal reaction will balance its weights cost component. Then for the block B, we'll have weight minus 2T is mass into acceleration. And finally, for the block C on the other side, we will have T is equal to mass into acceleration. Normal reaction balances the weight. That's not really a significant equation. So let's put in the values here and just quickly write these equations. So T plus this one's weight, which is 20 newtons, into sine 37. So that's 20 newtons into 0.6. So that's 12. Minus the kinetic friction on E. Now kinetic friction on E will be mu into normal reaction on E. So mu was 0.5, and the normal reaction on A will be its weight cost component, so 0.8. So 0.5 into 16, so that will be 8 newtons. So this should be equal to mass of the block A, which is 2 kgs into acceleration of E. So this is our second equation with the numerical values substituted. Similarly, the third equation we already discussed. The fourth equation, the weight of B is 30 newtons minus 2T is equal to 3 times AP. So that becomes our fourth equation. And finally, P is equal to mass of C, which is 1 kilogram, into acceleration of C, which is AC. So this becomes our fifth and final equation. Now, one easy way of solving such a system will be, we can write all the accelerations in terms of tension. So we can see from equation 2, acceleration of A can be written as T by 2 plus 4 by 2, so that's 2. Okay. And from fourth equation above, we can write acceleration of B as 10 minus 2 by 3 T. And from the last one, acceleration of C is equal to T. So we can now substitute these values in the constraint relation. That's the first equation. So acceleration of A plus acceleration of C is equal to twice of acceleration of B. So we just substitute this. We have T by 2 plus 2 plus acceleration of C, which is just T, is twice of acceleration of B, which is this much. C half plus 1 plus 4 by 3 from this side become 20 minus 2, so that's 18. So this becomes the tension, and then substituting this back in the above equations, we will get the accelerations. So for example, now you can see that acceleration of A is T by 2 plus 2. So that will become 54 by 17 plus 2. Okay. Acceleration of B will come okay. So you can see the acceleration of A and acceleration of B are like this, and acceleration of C is directly equal to T, so that's 108 by 17. So these become the individual values. Okay. Okay, now next up, we'll look at a very interesting problem to understand the both the nature of friction as well as a bit of three-dimensional vector algebra. So I'll put up the question and we'll discuss about it.